A story about expression microarrays would be incomplete without mentioning Vooma. When you go into Geo2R and do some analysis, have these nice plots, but then something bothers you about options and you go here, click, 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 and here it is a choice, apply limma precision weights. You can also click for more. Then it will tell you that it's about mean variance relationships estimation, which is a bit vague, but some sort of helpful. It goes about this particular plot where you see relationship between average log expression of genes and standard deviations of the same genes. In ideal case, the cloud is compact, sausage-like, no big differences between lows and highs, but very often there are differences, and sometimes cloud looks quite weird, and then you might think, okay, probably I have to switch on this option in order to make those calculations more accurate. A little bit of a history. First it was a Voom, not Vooma. It came with this paper from the same group, Gordon Smith, in 2014, and it was about RNA-seq analysis, even though Voom and Vooma, they are both functions sitting in limma, which you might think is only about microarrays, but it isn't. There is also a part dedicated to RNA-seq data. PubMed doesn't show any result on Vooma search, and in a geo page there is no reference to this method as well. And you might think that Voom and Vooma are kind of the same, but it's not the case. Voom is a complex function which includes log transform and optionally normalization of the data, whereas Vooma has no normalization option, neither log transform. It only looks for relationship between gene expression and variance, and it is specifically designed for microarrays, whereas Voom is designed for RNAseq. We can test both in one script. Usually it's not possible, but we have this strange case, which you can call lucky. These are microarray data, but background was removed and data are shifted down. So it looks a little bit like RNA-seq data, whereas formally it is microarray data, and we might ask ourselves, what should I use in this case? What is better, Voom or Vooma? Let's try to find out. So I took this GAC number and I wrote the script. So load the library, limma. So load the data, make a sample table out of the column names. It's useful, handy. Then we can check the original expression data in a log transform scale. That's a famous case with negative values, which has to be corrected, shifted upwards a bit. The minimal expression is 0, which is like in RNA-seq data. So let's do a manual dispersion plot. Means are simply raw means for expression of genes. Genes are in rows in this data, and standard deviations for matrix comes from this matrix stats package. It's useful. Can do SDS for entire matrix in one go. And here is the plot. without telling much, you simply notice that it's very different compared to what we will see later on. It's simply for our knowledge how raw data would look like. Then we do a background correction, and now histogram will look much better, no negative values, that's fixed. Then we check the box plot and see that data are not normalized and still has to be. Then we define a design that we are interested in finding difference between cell types, between LT and ST. This is a differentiation set. Okay. And now we try 3 different options. First we can say, let's try Voom, but if we try Voom, then we can use expression data as there are without normalization, without log transform, because log transform happens within Voom no matter what. And you can also add normalization method, in this particular case quantile. And so this is interpretation of the Voom, the very same log transformed counts. It's not original data, it's transformed data by Voom. There is still a change in standard deviations across the high and low average expressions. Well, now Voom knows how do they depend on each other. Then, according to the recipe, we run the fit, and then from this line you jump down to here. So that's the very first option we do. So we confirm that it's we seek for a difference between cells LT-HEC and ST-HEC. It's hematopoietic stem cells, long-term, short-term. Then we add gene IDs. Then we do a contrast. Then a second fit with the contrast. Then we go through the estimation of p-values based on all these fits. And then we reduce a table, and you can choose out of many columns. I prefer this. This is still very big table for all the genes, and we make it short based on decide tests. I decreased the p-value from standard to a little lower to reduce the final list of differential genes and hopefully make it more robust. Note that LFC is also included in decide tests, which is log2 FC. I say the minimal is 1, which means a twofold difference at least. All right. Then we check the summary. So there are 134 down. This number is not significant, and these are 661 up. So not to do it all over again, I use DT as decide tests to make my tops with the genes, because DT is only deciding how many, but it's still not telling who there are. Option is Voom, and this is the funny way of assigning my list of differentially expressed genes to the option I have chosen. It's a good remedy against poor memory. If you come to here and you ask yourself what was it again, then option will help you tell that, oh, it was a Voom option. Okay. And now we go up, we repeat this block. Now we did a Voom and we have a list. Note there are some empty names because not everything is has a name. Now we go to Vooma. As I said, you cannot use express gset data. You have to do normalization and log transform first, and that's how you define log normed. And then you say option is Vooma, and then you do Vooma. You notice that it's a little bit shifted, but overall the same. And then we say fit, and in LM fit we say V, which is now for Vooma. And we repeat the business down there, the common part again, now somewhat faster, and we do assignment. Alright, now we have it to Voom and Vooma. By numbers it is pretty close, but later we will check how close it is by name. Now we have an option, standard fit, so no Vooma, just do it as is. In this case, again, you use a log normed data. Design is the same. And fit doesn't have a visualization. You have to call it plot SA for fit. And again, the cloud is somewhat similar. Why not? And we repeat the common part. And decide tests and assign standard. You see that although clouds are pretty similar, probably the same, the choices of Voom and not choosing them affects p-value estimation. So instead of 700 plus, you have only 71 if you don't use Voom or Vooma. And it's not only for this particular case, it's a common trend that every time you apply Voom or Vooma, your list of differential express genes will be bigger. Now let's compare by name. We call Euler for Venn diagram, and then we declare list that standard fit, Voom fit, and Vooma fit. And then we do Venn, and then we plot it. And here it is a bit of the trouble again, that even though by numbers Vooma and Voom are close, by gene names they are not close at all. And since our data are microarrays, it is also not worthy saying that all what you find in a standard fit are all included in Vooma fit, and Vooma is made for microarrays, not Voom. And based on this, you can also say if you want more genes on your list, even with the weird microarray data, you still apply Vooma, not Voom. So if it was a story with morale, the morale of the story is that if you want to fix some trouble in your microarray data, try Vooma, not Voom. Although my personal feeling about these extra tools, which are basically aimed to fix some glitches in your data, is that those extra tools are somewhat dangerous. Using Vooma or Voom, you can enlarge the list of differentially expressed genes, but there is no guarantee that you fix your data. After all, you still have to do work comparing different data sets of a similar analysis and then figure out what is the most consistent between all of them. In other words, it's better to have a good data rather trying a good tool to fix a bad data. Yeah, something like this.